Hello, Maurieo! In this video, Beam Me Up Fred, we're going to be looking at beams. So let's crack onto it and let's get our first beam up there. So here we are. We have 3 beams in this instance here, and the 3 beams are spaced like so. And on top of those beams we have a floor, and those beams are supporting the floor, and each of those beams is a set distance apart called the spacing. Now the focus of this video is going to be the UDL, and we're going to be able to determine in this video the self-weight of the beam, given as, in the first instance, the total weight and length. So the total weight of the beam and the length. From that we're going to work out the self-weight and the UDL associated with that. And then we're going to work out the self-weight given as density, a density and a volume. Work out the UDL. Now the self-weight is just the weight of the beam itself, that it has a UDL. But also, if we look at our diagram, we can have imposed loads on the beam. It might be, for instance, the weight of the floor would have its own UDL, but then we could also have imposed loads. We could have a dead load, like for perhaps a fridge or a freezer resting on the floor, and that has a UDL. And then we could have a live load, which might be people walking backwards and forwards, or a car perhaps, or something that comes and goes. So all of these loads have their own UDL, and when we want to look at a beam and how it's performing, or how it might perform under certain conditions, we need to determine each of the individual UDLs and add them all together so that we can see all of what's happening with the beam. Now by now I'm hoping that you are asking the question, what the hell is a UDL? What the hell is a UDL? Well, I don't think I can go too much further without telling you. So here it is. What does UDL mean? Well, it means Uniform Distributed Load. UDL. Uniform Distributed Load. A little bit wiser, but still need to know a bit more. Well, what units is the UDL measured in? Well, typically it's measured in kilonewtons per metre. Well, we know that kilo means 1,000, as in kilogram is 1,000 grams, and kilometre 1,000 metres. So kilonewtons must mean 1,000 newtons. Wow. What the hell's a newton? Well, the newton is a measure of force based on Sir Isaac Newton's second law of motion, often expressed as a formula: F equals ma. F is the force, m the mass, and a the acceleration. So the plot thickens. So moving on, we'll see if we can find out a little bit more about the Newton. A Newton is the force of a 1 kilogram brick or object, or anything that weighs a kilogram, accelerating at 1 metre per second per second. Per second. Bit hard to say really, but probably known as metre per second squared. Now, a 1 kilogram block on a desk is pulled to earth by the force of gravity at an acceleration of 9.81 meters per second squared. So using Newton's second law of motion, F equals ma, F equals ma, we have 1 kilogram times 9.81 meters per second, the force that gravity is pulling the 1 kilogram brick towards the earth, and that will have a force of 9.81 newtons. 9.81 newtons. So, if we were to have a 1 ton weight on our desk, we would probably have no desk. But let's just surmise that our desk can handle a 1 ton weight. So that's 1,000 kilograms. 1,000 times 9.81. Move the decimal point 3 places to the right and put in any zeros to fill in any gaps. 9810 newtons. 1 ton, 9.9810. That's 9,810 newtons. So that would be the UDL. No, that would be the that would be of it just sitting on the desk, the force that was on it. 5 tons, of course, would be 5 times 9810, which would be newtons, and that's 49,550 newtons, 49,550 newtons. Okay, so that's newtons, and we see we're looking at a 12 meter uniform B weighs 5 tons. That's the metric ton, which is 1,000 kilograms. What is the UDL self weight of the beam? So we know that the force that 5 ton beam is exerting on whatever it sits on is 49,550 newtons. So let's move ahead. I feel we're getting closer to the elusive UDL. Now the UDL, of course, as we know, is measured in newtons per meter. So we've got 49,550 newtons, got a 12 meter beam. Pretty simple, really. 4129.167 newtons per meter. That's 49,550 divided by 12. 4129.167 newtons per meter. But typically, because the newton is quite a small measure, or a small amount of force, we measure these in kilonewtons per meter, and that is 4.129167. That's a lot of decimals, and we don't really need it, so we can, that's approximately equal to 4.13 kilonewtons per meter, to obviously 2 decimal places. So this is where we have the first scenario, where we have the length and weight of the beam. So that brings us to the second scenario, where we have the density and volume of a beam, and we can work out the UDL for that. This is scenario 2 that we mentioned at the beginning of this video. And so our answer, the question that we're going to be using is, what is the UDL self weight of a uniform concrete beam 200 millimeters wide by 500 millimeters deep? We know that concrete weighs 2.4 tons per cubic meter. Now the UDL is measured in kilonewtons per meter, so let's look at just 1 meter length of beam. Dividing by 1, very easy. Very easily done. So what is the volume of a 1 meter length of the beam? 500 millimeters deep, 200 millimeters wide. So as we know, volume equals length times width times depth or distance, or 3 dimensions. So what have we got? We've got 1 meter times 200 millimeters times 500 millimeters. Oh, off we go. Let's multiply that out. Let's not. What we have here is we have got mixed units. Meters, millimeters, millimeters. We must always have the same units. So we're going to convert the millimeters to meters. 200 millimeters, 0.2. Move the decimal point, and there's not one shown there, but we know it's there. 3 places to the left. 3 places to the left. So we get 1 meter times 0.2 meters, 0.2 of a meter times 0.5 of a meter. Multiply that out, and that comes out to 0.1 of a meter. 0.1 of a meter, cubic meter. 0.1 cubic meters. The volume of 0.1 cubic meters. So what will 1 meter length of beam weigh? Well, it'll weigh 0.1 cubic meters times 2.4 tons. Right, and that is 0.24 tons. 0.24 tons, or 240 kilograms. 240 kgs. 240 kegs. So, what's the UDL? Well, UDL, 240 kilograms times the acceleration due to gravity, 9.81. Multiply that out. 2354.4 newtons per meter. But we want kilonewtons. Move the decimal place 3 places to the left. On you go. Between the 2 and the 3. 2.35 kilonewtons per meter to 2 decimal places. Okay. And there we have the second scenario. We've worked out the UDL self-weight of a uniform concrete beam given the dimensions, so we can work out a volume and a density. So now it's on to the third and final scenario that we talked about at the beginning, and here it is here. And this is, what is the UDL of a 2 kilopascal imposed load where, and we need to just perhaps tidy up our where there. It's missing a bit of an E there. So see if we can get an E in. There we go. Where the beams are spread or are spaced at 1.2 meters, as shown in the diagram here. Now we've got this 2 kilopascal imposed load. Well, hang on, Pascal. Where did that come from? No, not from the lolly shop. Pascal, Blaise Pascal, quite famous mathematician. Now, what's a Pascal? Well, 1 PA, or Pascal, is a Newton per meter squared. 1 Newton per meter squared. So, if we've got 2 kilopascals, 2 kilopascals is actually equal to 2 kilonewtons per meter squared. 2 kilopascals is equal to 2 kilonewtons per meter squared, because a kilopascal is 1 newton per meter squared, so 2,000 of them, or 2 kilopascals, 2 kilonewtons per meter squared. So let's have a look at that. So we've got 2 kilonewtons over meters squared. Now we know that the UDL is expressed in kilonewtons per meter, and we've got kilonewtons per meter squared. So if we multiply, as you say, it's 2 kilonewtons per metre squared, and if we multiply that by the 1.2 metres, we can see that if we just cancel out our units, we get 2.4 kilonewtons per metre, because this is over there. So the 2 kilonewtons is over the metre squared, and if we multiply that times the spacing, the 1.2, that'll give us 2.4 kilonewtons per metre, which is equal to our UDL, because our UDL is measured in kilonewtons per metre. Now note, I've used the spacing, but in reality what happens is if we go halfway between each beam, that's the area that's worked on, each beam covers. So, but that's actually equal to the spacing between the two beams. So that's how that's all worked out. So there you have it. There you have it, the UDL in 3 different scenarios. One, in the first scenario where you're given the length of the beam and the weight. In the second scenario, you're given some dimensions that would enable you to work out the volume of the beam and the density. And in the third one, where we're working out the UDL, you're given the imposed load on the beam and the spacing of the particular beams, and we're able to work out the UDL. Remember that in each situation we need to work out all of the UDLs that are acting on the beam. We calculate them individually and add them up to address the total uniform distributed load on a beam in a particular situation.